to Sangil for the invitation not to speak, or not just to speak, but for the entire week. And you've been very hospitable while I've been here, and it's been fascinating. I've never been to Korea before, so this is my first time, and I'm enjoying it very much. And I sort of learned a tiny amount of your alphabet to be able to write my name, which is an approximation of my name at any rate. So it's the nearest I could get. Actually, your administrator Nari helped me with this, because I came up with my own suggestion, and she replied going, "No, this is better." So thank you to her. So yeah, I'll say something very quickly. I'm from the Open University, which is in England. It's a different university. It's a distance learning university. So we have maybe 140,000 students. And in math we have maybe, I'm not precisely sure, but maybe 4,000 or 5,000 students. So we're a big place, but we don't ever see any of our students, which gives me the freedom during term time to come away to Korea, because I don't have to lecture ever. So, okay, so that's the Open University. This work, at the end I'll have 3 references to various joint papers with various authors, so most of this is joint work with other people, but really what I'm talking about here is a sort of intuition behind some of the ideas, but that appear in these papers. So that's the right way. Okay, so just to be totally precise, what we're starting with, we're going to have we're thinking about graphs with some vertices and edges. They're going to be undirected, there's going to be no loops or multiple edges, just straightforward plain normal graphs. And I'm particularly interested in the induced subgraph ordering. So here's a graph, and if I'm looking for the induced subgraph of it, that says that I'm looking for a subset of the vertices where the edges on those vertices give me an exact copy. So there is this graph as an induced subgraph of there. In particular, I'm not allowed to delete edges on their own. Whenever I delete an edge, I'll have to have deleted one of the vertices, one of the incident vertices. Okay, so the induced subgraph ordering is pretty much all I'm thinking about. And I'm going to use the term class just because, well, when I visited Dartmouth College in the US a few years ago, and Pete Winkler there is a great fan of using terms with one syllable in them. Okay, so I'm going to use the term class instead of hereditary property, because class has one syllable. Okay, but what I'm really thinking about today, I'm thinking about collections of graphs, hereditary properties of graphs. So by that I mean, if inside this class of graphs I have a particular graph and I have an induced subgraph of that graph, then this thing must also be in the class. Okay, so whenever I have some graph in, all of its induced subgraphs must also be in the same class. So as an example,
you also want to assume that isomorphic graphs are inside.
Yeah, so isomorphic graphs should also be in there, I suppose, as well. Yeah, right. So I'm from a place where isomorphisms don't ever bother me. So yes, you're quite right. So for example, if you don't know what I'm talking about, then for example, a set of all planar graphs is a hereditary property, as well as being properties in other senses as well. Because of course, if I delete some vertices from a planar graph, I'm not going to create something that's not planar anymore, right? Okay. So for clique-width, we have a little game. We have 4 operations which I can use to build a graph, and for these 4 operations I'm given a set of labels capital sigma. So the 4 options are that I can create a new vertex with one of the labels from this set. I can take the disjoint union of 2 things I've constructed before and just stick them next to each other. They will have labels on them at this point. I can join all vertices, I can put an edge between all vertices with a label I and all vertices with a label J, but I and J need to be distinct in this case. Or I can do a sort of relabeling. Okay. So the idea is I want to build a graph, and in the end it's going to be unlabeled, but I'm using these labels as sort of auxiliary tool in order to construct my graph. So here's a little example. let's try and build this. Well, I probably won't get as far as that because it's too big, but you'll get the idea quickly enough if you haven't seen this before. So I'm going to show that you need at most 3 labels to construct this. And let's start with sort of some of these leafy bits. So if I can take sort of 2 leaves and each give them the label 1. Then I bring in a new vertex, which is going to have the label 2. I'm not allowed to make things, so option number 3 here says that I is not allowed to be equal to j. So I'm not allowed to bring in label 1 and say make it all adjacent. So let's have label 2. And then I want to use my option number 3, joining. I'm going to join 2 to 1. So that puts those edges in there like that. So I've created a tiny binary tree now. And now I'm allowed to use the disjoint union operation to make a copy of this. So I can say, well, I've already built one of these, so I can build as many of these as I like and just put them in next to each other. And then to create the next part of the binary tree, I want to sort of glue these together. So let's bring a new vertex in. I want this to be adjacent to both of these. But if I give it label 1, then I'd end up putting these, when I put those edges in, I put in these ones. So I need to give this a label 3. And then I say join 3 to 2. I can now do a little bit of housekeeping because these 2 vertices are never going to be adjacent to anything more. So I can give those the same label 1 as these ones down here, which are also never going to be used before. Okay, so now I've created a small binary tree. I can make a copy of that, like this. All these things have that label by the time I've finished, and a 3 at the top. And well, now the label 2 is available for me to use, so I can put the 2 up here and do that, and then I can label those to 1, and so on. Okay, so I can definitely do that using 3. Okay, and the clique width of a graph is the size of the smallest set of labels that you need in order to build a graph. Okay, so I've shown you that the clique width of a binary tree is at most 3. With some more argument, you can convince yourself that you can't do it with just 2. Okay. So, importantly for us, if I have an induced subgraph of another one, then the clique width obeys the inequality that you want it to obey. So, whenever I go to an induced subgraph, the clique width certainly can't go up. And that's going to be quite useful, in particular if I'm thinking about a class. Remember, a class is a hereditary property. Then the clique width I can sort of think of as being the maximum over all graphs in my class of the clique width of those graphs. Now, these classes generally contain infinitely many graphs, so this is probably rather poorly defined. So I've sort of qualified it with if this exists at the bottom, just to be a little bit lazy. Okay. So, why are we interested in this construction? Well, there's this meta theorem from 2000, which is the thing we put in our grant proposals. In the UK, when we write grant proposals, we have to talk about impact and applications of our research to industry. So we come out with the same story every time, right? So when we're talking about clique width, we say, well, in any class where the clique width is bounded, so that's the definition. Too far. So where every graph has clique width needs at most some fixed finite number of labels, then any property, by which I mean any algorithm, anything I want to ask about a particular graph, which I can express in something called monadic second order logic, can be determined in polynomial time. Okay. So there are people in this audience who know a lot more about monadic second order logic than I do. In particular, the idea is I'm allowed to quantify over vertices. I can construct sentences that quantify over vertices and edges, and I can also construct sentences that quantify over sets of vertices. Okay, but not sets of edges. That will come in a minute. Okay. Importantly, really, these properties include lots of problems which are normally NP hard. But when you're in something where you have a clique width expression, you can then come up with a nice I mean, I say polynomial time, but it's really linear time, right? Yeah, okay. So the reason why this thing sort of came around in the first place is, in a certain sense, you can think of it as a generalization of tree width. Generalizes is maybe slightly unfair because it's sort of different. But in particular, tree width, which I'll say a little bit about in a minute, was critical to the proof of the graph minor theorem, which is this, as you all know, celebrated result. Okay. But unlike tree width, clique-width is something that can cope with complete graphs. So I can build a complete graph using just two labels, right? I can do it just one at a time. There's a vertex 1, here's a vertex 2, make it adjacent, relabel to 1, add another vertex, labeled 2, make it adjacent, relabel to 1. So I can add one vertex at a time using just two labels, and I can create a clique. But for tree width, the tree width of a clique is, well, m minus 1 if you have m vertices. Okay, so what is tree width? I'm not really going to say very much about this. In a rough sense, I'm not going to define it. It sort of gives you a measure of how much like a tree the graph is, and you can sort of imagine that a clique is really not very like a tree at all, so that's why that's really bad. Okay. So something similar as to the theorem we have for clique width exists. If you have bounded tree width, then all problems in MSO2 have polynomial time, and MSO2 is where you're allowed to quantify over edges as well, so you have a greater expressive power. So there are more algorithms here, okay? But then the cost is that, of course, you can't cope with any class which has big cliques in. Okay. So this is sort of maybe one of the motivating points. So for tree width, we have this nice characterization of when a minor closed family of graphs, so some other collection of graphs, you have a nice characterization for when the tree width is bounded, and that is precisely if it doesn't contain all planar graphs. In other words, the forbidden minors of your minor closed family must include some planar graph. Okay. So in a sort of informal sense, the collection of planar graphs is the unique minimal family of minor closed graphs when you're thinking about tree width. So here's a naive question, and if you don't know already, you'll see why it's naive. Can we get something similar for clique width? Is there a way of finding, a family or a small number of families or some other characterization of classes, i.e. now hereditary properties, which characterize the boundary between unbounded clique width and bounded clique width? Okay, so that's kind of what I'm looking at today. So for the rest of today, that's a sort of a generic introduction, if you like. We're going to look at some cases where the clique width's bounded or it's unbounded. We're going to look at, in particular, I'm looking at the minimal classes with unbounded clique width. Well, planar graphs are this minimal family for tree width, so that's the place to look for if you want to answer the previous question. And I'm going to show you how permutations, which is the area that I come from originally, it's where I did my PhD in, how that gives us some insights into what's going on here. And then it becomes a bit of a compendium of things at the end. So the first thing is I'm going to start looking at something called linear clique width, which I'll say more about later. And in particular, how the unboundedness of linear clique width is often actually the same as unboundedness of clique width. Okay, remarkably more often than you would expect. And then if there's time, which there probably won't be, then I'll say something about well quasi-ordering, which is my favorite subject. Okay. So, if I have a class, is its clique width bounded? That's one question I want to ask. So, the reason why you sort of think of clique width as a generalization of tree width is, well, if the clique width is at most this, right? So that's a result from 2005. And seeing as I'm here, I couldn't possibly give a talk about clique width and not mention rank width, given we have the inventor of rank width in our audience. So we have this sandwich, right, where clique width is at least the rank width and at most 2 to the rank width plus 1 minus 1. Okay, and actually, as well as this, the reason why this is important is whereas it's kind of tricky, well, in fact, it wasn't really known how to get to know whether the clique width for a particular graph was bounded, right? It was sort of, there was an algorithm which gave you some function which involved log in the number of vertices of your graph. When rank width came along, you were able, you could remove the need to have a clique width expression before you ran any of these algorithms. That's probably the best way to say it. There's an expert in the audience, ask him. Okay. So here's some classes of bounded clique width. If I think of the class of all forests, and the clique width of forest is 3. I mean, it's at most 3, but so some small ones it's 2. And another class I'm interested in is the class of cographs, which are going to appear a couple of times. So cographs are constructed from a single vertex, that's what this dot means, by successively taking disjoint unions of joins of smaller cographs. So the idea is that, well, I have a single vertex, and then I can take the disjoint union, so that's one graph. I can take the disjoint union of that, which gives me 2 single vertices, or I can take the join of 2 single vertices, and so on and so forth. And in general, I can take any cograph and any other cograph and just stick them next to each other, or I can take any cograph and any other cograph and join everything in between. Okay. So it gives me this recursive construction. And there are all sorts of different characterizations of cographs, but in particular they are the class of graphs, the largest class of graphs with clique width 2. Okay. So much for bounded clique width. When do we get unbounded clique width? So here is something which is very, very loose, but here is an infinite grid. But my grid here is going to have a fixed height, so fixed height k, but it can be as long as it likes. Okay. Now I didn't bother to work out exactly what the clique width of such a arbitrarily large graph is going to be, but basically, you know, if I can construct some piece of this thing, and then I want to glue it onto another one by taking disjoint union and then sort of joining bits up, I only need to remember the labels to create the edges, just to glue those k pieces together. So I'm going to need some multiple of k labels to do this, but it's definitely big O of k. Okay. So the reason why I'm saying this is the intuition for unbounded clique width is sort of somehow 2 dimensions of complexity. Okay, so here I have 1 dimension of complexity. It goes this way. If I tried to glue this graph together, a top piece and a bottom piece, then I'd have arbitrarily many edges which I'd need to glue together, and they'd all be different. So I'd need a different label for all of them. So in particular, if I take an n by n grid and let n get arbitrarily large, then the clique width grows with n. In particular, it's exactly n plus 1, according to Colin Bipartite. Okay, so that's the intuition behind unbounded clique width. And basically, all of these examples of classes of unbounded clique width have this sort of 2-dimensional property. Okay. So there are various examples. Some of the early ones, unit interval graphs. So these are graphs which you can construct by starting with let's take a number line, and I suppose I should tell you how long a unit is. There we go, that's how long a unit is. And now I'm going to take a bunch of intervals of this thing, so like this, and so on and so forth. And each of these intervals corresponds to a vertex, and vertices are adjacent if they have non-empty intersections. So that vertex would be adjacent to that vertex, to that one, and that's to that one, and that one, and that one. Something like that. Okay. Split graphs are another class of unbounded clique-width. We'll see those again later, but basically any graph which has a partition of the vertices where it's a clique on one side, an independent or stable set on the other side, and any edges you like in between. Bipartite permutation graphs, I'm definitely going to say more about those later, so I'll say no more now. And then the only thing that's so maybe this last bullet point first, any modification to the n by n grid, you can just, I don't know, put cliques on the columns or on the rows or both at the same time. There are all sorts of different modifications you can do to this, and the same argument that was used, I mean, I didn't give you an argument, but the same sort of heuristic and indeed the same actual argument works. So the only one here which is different is this one. So any class which has superfactorial speed, by which I mean asymptotically more than n to the c times n labeled graphs of order n for any c. So factorial speed would be there exists some c that there are asymptotically n to the cn graphs. Superfactorial means that no matter what c I put there, I can asymptotically find more graphs than that. Okay. And the point is, this argument here, the reason why that's different is you have a lot of graphs here, a really lot of graphs. And there just are not enough expressions of clique-width in order to construct that many graphs. So it's a simple counting argument, and that's it. Okay. So we have lots of examples of classes with unbounded clique-width. And we want to know, in particular, which of these are minimal, or are any of them minimal? Is there some nice characterization? Is there some way of knowing what these minimal classes are? Okay, so there's somewhat fewer of those. Maybe because there's more to prove, right? You can't just show they have unbounded clique-width. You also have to show that any proper subclass of this has bounded clique-width. So it's kind of harder. So there are two from 2011 by Vadim Lozin, unit interval graphs, that's these ones, bipartite permutation graphs, which I still haven't told you about. And then split permutation graphs and bichain graphs are two new ones, which I'll say a bit more about in a minute, which is joint with these various authors. So the general method to get minimality, once you've, well, I suppose you take your class C and you try to get some kind of structural characterization of that. You want to say every graph looks a bit like this. Okay. And once you've got this, every graph looks a bit like this, you say, well, I want to find some kind of universal graph, un, which contains every graph on m vertices as an induced subgraph. So un might have considerably more than m vertices, typically n squared or n cubed. So I suppose, for example, if I want to look at a I'm going the wrong way. So if I wanted to consider an induced subgraph of an n by n grid, then the n by n, or of an arbitrarily large grid, then the n by n grid is a universal graph for any induced subgraph of a bigger grid on m vertices. Okay. So we have these universal graphs, and in particular, you show that the clique-width of your universal graphs is some function of n where it grows with n, right? So typically it's n, or maybe n plus 1 or something like that. As long as it grows to infinity, I don't mind. So for our grid graphs, the clique-width was n minus 1, if I remember correctly, if I was paying attention. Okay, so and then once you've done this, you come up with some technical lemma. So the point is, once you've got this universal graph, if you go into some kind of subclass of this, you have some additional forbidden restriction, you have some additional restriction on your class, that kills off some universal graph and every universal graph that's bigger than it. And then you have some technical lemma which basically says that because you've killed off all these universal graphs, your clique-width is bounded. Something like that. Okay. So now I need to say what permutation graphs are. So I'm going to think of permutations as just an ordering of the numbers 1 up to n. So here is the numbers 1 up to 8 in a permutation. Okay. And more importantly, I'm going to plot the points. So that's the 4th point, that's 1, 2, 6, 3, 8, 5, 7. Okay. And to this permutation, I'm going to make a graph. Now, the technical definition is down here. Whenever I have a point, one point to the left of another one, and these points, the one to the left is higher than the one to the right, I'm going to put in an edge. And if the one to the right is higher than the one to the left, then I'm not going to put in an edge. So I do this. Okay. So I now have a graph. If I ignore the grid and I take each of these points to be vertices, I have these edges, and I've constructed a graph. And just to be certain that we know what's going on, if I have the permutation n down to 2, 1, well, that looks like points all in decreasing order, then I can create a complete graph on n vertices. Okay. So there is a permutation graph, defined here as being any graph that can be constructed from a permutation in this way. Now, there were, in an earlier set of these slides, I had alternative characterizations of them, but that's a distraction here. There are other ways you can describe permutation graphs, okay? But this will do for me today. Okay, so as well as for graphs, we have the induced subgraph ordering, which says when I delete vertices and all the incident edges. And for permutations, I have a completely analogous ordering. So I have a partial order. I don't need to worry about isomorphisms here, see? So here is a smaller permutation. And if I look at the red points on the right-hand picture, they're in the same relative ordering. So in particular, if I rubbed out these black points and then kind of rescaled the axes appropriately, I'd end up exactly with the picture on the left. So what's important here are the relative orderings of the things going from top to bottom, or from bottom to top, and from left to right simultaneously. Okay. So this defines a partial ordering on permutations of different lengths. And just to sort of reassure ourselves, if I draw the graphs of these two things, if I look at the induced subgraph of these red points, which corresponds to, I suppose, an embedding of this smaller permutation in the bigger one, then indeed the graph of this is exactly equal to the graph I get of those points. So the permutation containment relation, when I turn it into graphs, preserves the induced subgraph ordering. Okay.
But is the converse may not?
The converse is not true, right? So in particular, this graph here has two components, right? So this point here is not adjacent to any of this one, but I could put this point up here if I wanted to go backwards. So there's the mapping from permutations to graphs is many to one. So in particular, if so if I've given this graph, which consists of P4 plus a single vertex, I could reconstruct a permutation out of that with that point up here. And that is not, well, maybe it is. This is probably a bad example because, yeah, it's not in there, okay? So yeah, the reverse is not quite true. You can sort of control it sometimes to try and fix it a little bit, but that's not true. Okay. So when we had a graph class, which is a hereditary property of graphs closed under the induced subgraph ordering, I can similarly define a permutation class. I'm sorry, I've broken my one-syllable rule there. To be a hereditary collection of permutations, i.e. if some permutation is in the class and I have some smaller permutation that's contained in that by this containment relation, then that must also be in the class. Okay. And we have this characterization, which we call avoidance. So any permutation class, and this is true for hereditary properties as well, can be characterized in terms of their minimal forbidden induced substructures. So in particular, every permutation class can be written as AVB for some set B, which means the set of all permutations which do not contain any of the permutations in the set B. Okay. So here's my first example. AV321. So this is back to Vadim Lozin's theorem from 2011, and this is not how he proved it, but to me this is why it was obvious even before he had proved it. Okay. So he was wanting to prove stuff about bipartite permutation graphs. Well, the permutation 321, that's a decreasing set, corresponds to a triangle or a complete graph on 3 vertices, or maybe a cycle on 3 vertices, depending on your preference. So when I say that I'm going to think of all permutations that avoid 321, when I turn those into graphs, they're the set of all permutation graphs that have no C3. Now, all permutation graphs contain no cycles of length 5 or more. Those are some of the forbidden graphs of permutation graphs. So if I additionally forbid C3, I've become bipartite. Okay. So the class of 321 avoiding permutations, when I turn it into a graph, give me precisely the collection of bipartite permutation graphs. So that means if I know stuff that's going on over here, then I know stuff that's going on over here. And the good news is that we've known for a very long time what these things look like. So informally, let's keep that. Speaking a little bit informally, if I have something that avoids 321, that says, well, here's a permutation, and I scan from the left to the right. And as I go, I'm going to mark all the points that I see that are maximum so far. So the first point, wherever it is, will be a maximum. Then I'm going to scan for a while, and then there's going to be another maximum, and another one, and another one, and another one. Okay. So this region here is completely empty, and the rest of the permutations over here. So these are, if you know, are called the left to right maxima. Right. So as you read from left to right, you store the maxima. Now, if I've avoided 321, you want to...
Yeah, just close it. That button.
No.
No.
I'll just close it.
Yeah.
Yes.
No.
Yeah, right.
No.
Yeah, that one. Right.
I was assuming cancel was on the left.
It was the other way around.
Oh no, there's no one on the right. Yeah, you're right. Okay. Yeah. There we are. So so there's nothing in this region, left to right maxima. If I strip all these points out and think about what's left, well, if I see anything in this region down here that's in that order, then with one of these points I've got here, I see a 321. So once I've marked these points, everything else must be an increasing sequence. So in fact, the class of 321 permutations are exactly the things you can get by basically merging two increasing sequences in any way you can, okay, and respecting the fact that it needs to be a permutation at the end. And there are other ways you can characterize it. Oh, I've lost focus. So from this picture you can fairly quickly argue that actually you need to be able to draw your picture in this way. So it has this little staircase, and in each box you have a little increasing sequence. Okay, so this is still very much the union of two increasing sequences, but now you can sort of, even if they crossed over each other, you can sort of rearrange them so the ones on the top are always in one sequence. So all the points sort of sit in these little increasing segments, and they can interact in the row and in the column and in the row in any way they like. But for example, that box there doesn't interact with anything further up here. Okay. So, and this staircase can go on forever. It can be arbitrarily long. Okay. Well, if I turn that into a graph, it begins to look like this. Now, in Vadim's original paper, this was the universal graph that he was using. Okay. Now we knew that because so that becomes n, length n and height n here, and that corresponds to, so each column in this thing corresponds to one of these cells, and then as I step along to the next one, that's the second column, is that box, and then I move up, that's to the third column, and so on and so forth. And between these things we have edges that form a half graph between adjacent columns, and then there are no edges between anything that's further apart. So this is the universal graph that Lozin used, and it's immediately obvious from this picture here. That's why it should be the case. Okay.
So those dots are the points on the permutation, right? On the left picture.
Yeah. Yeah. So that's, yeah. So I mean, probably it's not actually a permutation. This is a sort of representation, right? So if I'd stick n points in here, and they would interleave perfectly with the m points in here, and then they'd interleave perfectly with the m points in here, and so on. Okay, to get my universal permutation. Okay. So yeah, this is a sort of loose representation of my permutation class. Okay. In the same way as for graphs, you might draw big blobs saying there's a clique in here, and then there's particular things between this one. This is kind of our similar representation for permutations. Okay. Okay, so I thought, well, another known class of unbounded clique-width are split permutation graphs. And actually now we can prove that they're minimal. Now, I didn't really tell you how the previous thing was minimal, but you know, the technical lemmas are too technical to, they're too boring for talks really. So if I take a split graph, which I remind you is a partition of vertices into a clique and an independent set, and I rubbed it out. And when I'm looking at the permutation graphs, I'm thinking about, well, the graphs that are in the intersection of the permutation graphs and the split graphs. Okay. So there are some things in there. So a split graph looks like a clique and an independent set and some edges. Well, for permutations, a clique is a decreasing sequence and an independent set is an increasing sequence. So I can partition my permutation into an increasing sequence and a decreasing sequence. So it looks like a sort of X. Okay. Well, actually, some years ago we knew what this class was. It's a class defined directly by avoiding 2143 and 3412, and of course those are the two permutations if you turn them into graphs that give you C4, which are precisely in addition to the forbidden graphs of permutation graphs that define the split permutation graphs. Okay, but in fact we knew more than this. In fact, years ago we counted how many permutations were of each length in this class, and we have various other structure theorems. Somewhat more recently, this picture of the structure of this class came out. So it's a bit similar to the staircase before, but now it's slightly different. So there are all these cells, and they sort of spiral outwards. So there's these things here which are allowed to contain increasing sequences, and these cells here which are allowed to contain decreasing sequences. And I sort of have this spiral that moves all the way around. All the way around like this. Okay. So I've told you a bit of a lie here. This is sort of the universal structure for permutations, except that actually I also need to take it with its flexion around the line y equals x, which spirals the other way, right? But still has this x shape. And those two spirals can somehow be nested inside each other. So for permutations the picture is complicated, but this reflection around the line y equals x, when I turn that into graphs, makes no difference. So in particular, when I look at the graph, I end up with something that looks like this. Okay. So this is something of a spaghetti. So again, each column is going to correspond to one of these cells. So when the columns are decreasing, then they need to have cliques, and that's what these sort of blue highlights can give you. And also all the cliques are adjacent to each other, so these dotted edges connect all the blue ones together as well. And then I have this half graph structure between them, going downwards for the first one, then upwards for the second one, and down for the third one, and so on. But I also have some more edges. So I have edges from these guys to be adjacent to all of the things over there, and so on and so forth. Okay, so I defy any graph theorist to come up with this as a structure of a universal graph in the world of split permutation graphs. But you know, if you draw some big enough permutations, this becomes fairly obvious fairly quickly. Okay. So here's something where the intuition of permutations really helps. Okay, and then you have your technical lemma says this is universal, has unbounded clique-width. If I kill it off, I end up with something that is bounded clique-width. Okay, now I can get from split permutation graphs into another class called bichain graphs, which are the union of two chains. Oh, I shouldn't have used the term chains here because we've been talking about chains all week, but these are different. Chains here should be half graphs, which are these things that sort of go down to the right. You've got half the edges there. Okay. So to get a bichain graph, all that's really important is that I start with my split permutation graph, and I get rid of this clique on these blue vertices and between the blue vertices. So, informally speaking, it's a bit like taking this sequence here, which formed a clique, and turning it into an increasing sequence. But in doing so, I've preserved where it is, so I'm no longer in the world where I've got a permutation graph. I've long ago left permutation graphs. However, I've left permutation graphs, but this sort of deformation, this local sort of flipping, allows you basically to use exactly the same arguments in order to prove that this is also universal for bichain graphs and that bichain graphs are minimal. And in fact, for various aesthetic reasons, we proved it for this one and said, well, therefore this one is also the case. Okay. So those are two new classes of graphs. Perhaps more interestingly, so we had, first of all, we saw this staircase for the bipartite permutation graphs. We saw this sort of spiral thing for the split permutation graphs. And these are all sort of long paths, right? So, you know, here's another long path that has a nice regular structure. Maybe that gives us something. Okay, there are all sorts of ways you could do this. So there is some suggestion here that there should really be a more general theorem saying if you have a long path that is sufficiently regular in the way you construct your permutations, then you can turn this into a graph class that is minimal with unbounded clique-width. There should be a theorem that says that. And maybe there will be eventually. And once you've done this, as we saw with split permutation graphs, you can mess around with some of the sort of global rules about your construction to create other graph classes that aren't permutation graph classes. So with that in mind, well, we have four minimal classes already. There's going to be a lot of them. Once you start messing around with this, we're going to create lots and lots of these minimal classes with unbounded clique-width. So, you know, the naive question at the beginning certainly was naive. If we're going to have a characterization, it's going to need to be much more relaxed than just saying this class or this class or this class. Okay, it's going to need to be much more a sort of generic. It has to have this kind of structure to it. So now I'm going to quickly talk about linear clique-width. So it's the same as clique-width, except I've made it a bit harder for you by getting rid of the disjoint union rule. So this means that in particular to add new vertices or to make your graph bigger, you only have one option, that is to add a new vertex with one label. You can't take, here's a graph I built earlier and put it next to the other one. You're just not allowed to do that. And the linear clique-width is the size of the smallest set of labels that you need in order to do this. And the reason why I did binary trees earlier is because I want to do binary trees again now. So let's start again. So we start the same way as we did before. Why not? This isn't really going to be a proof, of course, because I'm just going to show you that it gets hard, right? So I have two vertices with label 1, and I add a new vertex with label 2, make them adjacent. Now with clique-width, of course, I then just said, well, I'm going to make another copy of this. But I'm not allowed to do that. So either I could start constructing a new one, but I'm going to have to use label 3 because I can't use either of these because I'm about to create something else that's adjacent to it. And then I could put up here label 4, and then I guess I could relabel and do that. I can be slightly more clever if I just want to make this graph one bigger. I can actually go, I'm going to make a new vertex of label 3 here and make it adjacent to 2. I can now relabel that to 1, so I give myself an extra label. I can even then put in 2 vertices also with label 3 and put in a vertex here with label 2 and then say make 2 adjacent to 3. So there we go. Okay, so I can get away with 3 here, but if I want to go any further I'm stuck because I've used 3 up here and down here. And so next time, at some point in the future, I'm going to have to join that thing up to there, but when I do it, it's also going to end up being adjacent to there. So I can go no further with label 3. That's basically the idea. So if I want to go any further, I better have not done this and actually used the label 4 down here. Okay, so I thought I was being clever, but actually it didn't get me very far. Okay, so you need lots of labels for binary trees, and the bigger the tree gets, the more labels you need. Sort of roughly speaking, because I can construct little bits of this, but every time I reach a new junction I have to go and explore down that bit, and I have to remember where I am. Okay, and then so I remember where I am, and I need a certain number of labels to build this bit, and then I've done it, and I come up, and I go to here, I have to remember where I am. And now I've got a tree which is even bigger now, so I need to use more labels. Then I come back and I go to here. I have to remember where I am while I build this bit, and so on and so forth. So binary trees need lots of labels. So let's ask the same question. Minimal linear clique-width. Obviously, linear clique-width is a restriction of clique-width. So if your clique-width is unbounded, then so is your linear clique-width. And here's the interesting thing. So bipartite permutation graphs we know are minimal with clique-width. We also know they're minimal with unbounded linear clique-width. Okay? And this is actually a corollary of a paper in the future. There is a final draft available, except that the final draft keeps being turned into something else. So this paper has been rolling for about 3 years now. And really this paper is entirely about permutations, and you won't find this corollary in there. Point is we're counting 3, 2, 1 avoiding permutations, and we're showing that basically there's a way of encoding all these things in a very efficient way that allows us to prove that basically the encoding we're using is essentially the same as linear clique-width, so this allows you to squash down. And moreover, the encoding we're using here, if you do the work enough, this is already a fairly long paper for that one specific example, but the other minimal unbounded clique-width classes also have this property. They are minimal of unbounded linear clique-width. Okay. So I'd like to know if there are any classes which are minimal of unbounded clique-width, but not minimal of unbounded linear clique-width. Okay, I don't know any examples yet, but I can tell you about some things which have unbounded linear clique-width on their own. So when does a class have unbounded linear clique-width but the clique-width is bounded? That'd be a place to start to answer that first question. So we know, we just saw binary trees where the clique-width is at most 3, but the linear clique-width goes off to infinity. Now cographs have also been known to have unbounded linear clique-width since 2005. And you go, okay, these are 2 kind of very different classes, except they're not. So cographs are constructed by, I do still have something of a cograph here, by a single vertex, and I'm allowed to take a join or a disjoint union at every point. So let's just go straight to here. In other words, I can describe every cograph using some kind of binary tree, okay, where I have a plus node saying disjoint union, a dot node to be the join. The reason why I chose these symbols is that it made the nodes the same size in my picture. That's the only reason. So you might prefer to use different symbols. So this picture here says here are 2 vertices. Let's start right at the bottom, says take the join of these two vertices, let's put that edge in, that's what this thing does, then take another vertex and take the disjoint union, so that gives me those three vertices. So the position of the vertices on the right, I should say, are in exactly the same relative places as the ones on the left. And then it says take the join with another single vertex, that's this guy adjacent to all of those, and then on the right I have two which I take the join of, and then I just stick them next to each other. Okay. So there's a binary tree that I can use to describe every cograph. And the point is that in cographs, these trees can be arbitrarily high and arbitrarily wide. That's the same problem as with binary trees. Okay. So are cographs minimal with this property? Well, what if I said, okay, you're not allowed ever to join two arbitrary graphs. I can still make my tree arbitrarily high and arbitrarily wide using the disjoint union operation. Okay, I still have that in my ability. So the join operation, I can say, well, you're very limited, but I've still got my disjoint union. Or I could do it the other way around. And indeed, that's exactly what it turns out to be. So quasi-threshold graphs are defined by building graphs from a single vertex by disjoint union of two things I've got before, or by joining one new vertex adjacent to everything that came before. So actually this is the same class, and this is a quasi-threshold graph. So the point is that I still have the ability to use the disjoint union however I like, which means I can make my trees as high and as wide as I like. But the join thing is gone. And of course the complement of this class, where I take I can allow to take the disjoint union of one vertex with something before, or the join of two things, that's also minimal. But if I restrict these quasi-threshold graphs any further, then I am in trouble, because I'm either going to end up having to bound the width of my tree or the height of my tree, or if I've done a really bad thing, I end up bounding both, but then your class is finite essentially. Okay.
So do you, I mean, you need to have this adding edge operation, right? The add operation.
Yeah.
When you add a vertex, you either make it complete or incomplete.
Yeah, that's right. Yeah. Yeah. So I can add one new vertex, and I can make it complete or anti-complete here. But this is the way of building quasi-threshold graphs, not to be confused with the linear clique-width operation, where I can only add one vertex at a time. Okay. So yes, I've got two constructions here which are kind of conflicting with each other. Okay, but the upshot is that quasi-threshold graphs and their complements are minimal within the class of cographs. So any subclass of cographs has unbounded linear clique-width if and only if it contains all quasi-threshold graphs or the complement. Okay. So in particular, this means if you don't contain all quasi-threshold graphs, then we have a very precise structure. We can always delete one vertex, or you can always be found to be sort of little finite pieces of graph which you can pull off, which are very easy to construct, and you can do this at every step. Okay. So it really is about the trees. That's pretty much time up, I'm afraid, so I'm going to skip this, which I run out of time for again, and say thank you very much for your attention.